Okay, hi everyone. Back again with another data analysis video, and this is the last one I'm going to record in this kind of this series of videos that I've made. I've nominally called them common analyses. It's included kind of tidying data, wrangling data, visualizing data, getting descriptive statistics, and then a series of null hypothesis significance tests that are kind of most commonly used in frequentist classical statistical methods. This is the last video in that particular series. I'm going to go on and make a series of other videos looking at different data distributions and probably looking at different ways to analyze data using kind of Bayesian models, which I think would be quite interesting and useful. But for this, to finish this off, I'm still, the last couple of videos have been about multiple regression. This is the last one I'm going to do. It's also about multiple regression, and in this case, in the last video we did multiple regression. We looked at including categorical variables in the model. In this one, I will look at how you can include interaction terms, so the interaction between independent variables. So when fitting a multiple regression model, what we're doing is assessing whether scores on a scale DV can be predicted from scores on several independent variables. And we extend that linear regression equation by adding a new term for each independent variable. And we can include each IV in the model separately, but we may also believe that two or more of our independent variables interact in some meaningful way that will influence their relationship to the DV. So when running multiple regression analyses using stats models in Python, there are a couple of different ways that we can include interaction terms in the regression model. And what I'll do in this video is I'll demonstrate how to conduct a multiple regression analysis that includes the interaction between two of the independent variables as an additional term in the model. Okay, so let's crack on with that. So let's start by importing some software libraries. I'm going to import pandas, numpy, matplotlib, statsmodels, and scipy. And then I'm going to import some data. I'm going to use the same data that I used in the previous video, which is this kind of insurance data set. So this kind of data set relating to insurance expenses. I'm going to save it as an object called df. You can see we've got these different variables: age, sex, BMI, children, smoker region, expenses. And what we're going to look to do is see if we can predict health insurance expenses based on age and BMI of the participants. So I think this is health insurance data from the US essentially. So I'm going to fit this multiple regression model using stats models, and in the very first model, just to keep it nice and basic, I will include the two independent variables separately, so just as main effects essentially. So I'm going to call it model 1. We're going to use stats models formulas .ols, so the ordinary least squares method, and the formula we're going to use, specified in this kind of R formula style, is our DV expenses is a function of age plus BMI. Okay, so let's look at the model summary. We've interpreted these a few times now. It gives us a nice HTML output of the model results, and we can see from this output that we have a significant regression model and that both age and BMI are significant predictors of the DV, which is insurance expenses. So let's have a look at that quickly before we move on. So we see we've got F value of 88.66 and P is very small, less than 0.00001. Okay, and if we look at our coefficients table, we can see age has a slope coefficient of 241.9, BMI 333.39. If we look at the associated T statistic and P value for each of those predictors, they're both significant. So it's telling us they're both significant predictors to this model. Okay, so to extend this, we can also include the interaction between age and BMI to see if this is significant. And there are two ways to specify an interaction term in stats models when using R-style formulas. The first is what's known as the matrix version, and the second is the multiplicative version. I'll demonstrate each of these in turn because they kind of the results they give us are kind of different in some ways. So it's useful to know what happens when they use them. So I'm going to use the matrix approach in this particular cell here. And here you will note that the interaction term is specified by separating the two independent variables with a colon. So I'm going to call this model underscore int1, so interaction model 1. It's the same formula as above for that first model we just ran, but you'll notice there's a slight difference. We've added this additional term. We've got age plus, so our DV expenses is a function of age plus BMI plus, and then we've got the interaction between age and BMI, specified as age colon BMI. Okay. So if we run that, what you will see, if we go up and look at the first model, is our R squared is about 0.117, so about 11% variance explained. And our R squared here, by adding the interactions, is about the same, 0.118, still about 11-12% of variance explained. And we get a significant model again, so if we look at the F value and the P value associated with it, we've got a significant model. But note that using the formula specification above, like this, so main effect of age, main effect of BMI, interaction between. Using that formula specification, we get a coefficient for age individually, the main effect of age, a coefficient for BMI individually, the main effect for BMI, and a coefficient for the interaction between age and BMI. So you can see those there in the coefficients table. Gives us age, main effect of age, main effect of BMI, interaction between age and BMI, essentially. Yeah. So, and in this case, we can see that although individually age and BMI are significant contributors to model, there's no significant interaction between these variables when predicting scores on the DV expenses. So you can see that there. If we look at the coefficients table, our T values, you can see that age individually is still significant, BMI individually still significant, but age, the interaction between age and BMI, we've got a T value of 0.63, P is 0.528, so not a significant contributor to the model. The interaction term isn't contributing. So in relation to this data set, this would tell us that there's no relationship between BMI and age that influences insurance expenses, although it's the case that expenses increase with age and expenses increase with increasing BMI. It's not the case that BMI is related to age, and in combination that they can be used to predict insurance expenses. So combining the two doesn't predict insurance expenses. What I'll do now is I'll run the same model again, but I'll remove the individual main effects terms and we'll just include that interaction term. Okay, so running it again using the matrix approach, so with this colon, but this time leaving out main effects terms. So model interaction model 2, notice I've taken out age plus BMI plus age colon BMI, and now we're just saying expenses as a function of age interacting with BMI. All right, let's run that. We still get a similar R squared value. We get an F statistic that is significant, so we get a significant model. And this time we see the interaction term, this is our coefficient, and age interacting with BMI is significant. Okay, so we've got a T value of 12.99, P is less than 0.001. So on this occasion, what we see from the model output is that the interaction term is the only independent variable included in the model. So we left out the main effects of age and BMI, so those individually. What we still find is we have a significant regression model. Now the interaction term is significant. This is because this is the only variable we've included in the model. And these two variables still account for the same amount of variance explained in the DV. So we've still got an R squared of about 0.11, 11%. But if we were to run this model again and add the individual independent variables, the IVs, in individually, we find that this interaction term would become non-significant, as it does not explain anything beyond the variance accounted for by the main effects of the independent variables individually. So if we were looking at this model, model 2, and the one we did before that, if we were comparing these different models, we'd likely consider a model that just contained the individual independent variables, so no interaction term, as the best fitting model, as it would be the least complex and it'd still account for the same amount of variance explained. Okay, so that was kind of the matrix version using that colon operator. Now what I'll do is I'll fit the same models, but this time using the multiplicative specification in the formula. Okay, so note here for the multiplicative version, it's very similar in terms of syntax. I'm calling this model interaction model 3. Our formula is very similar, but rather than using the colon operator, we've replaced that by the asterisk symbol to represent multiplication. So now what we've got is our DV expenses as a function of age plus BMI plus the interaction between plus age times BMI, the interaction between age and BMI. Let's run that. And you see what we get is kind of the same as, what was our second model, was it? Sorry, our first model. You effectively get the same results as our first model, where we get a significant F value, significant model, and if we look, we've got a coefficient for age, main effect of age, coefficient for main effect of BMI, coefficient for the interaction. Only the main effects, we've got significant T values for age and BMI, but not for the interaction. So same results as we could expect. So we get the same output as we got for the first interaction model, where the main effects of age and BMI are significant predictors, but the interaction between them is not. Okay, so we should expect that to be the case. What I'll do now is I'll run this analysis again, but this time I'll only include the interaction term, age times BMI, age asterisk BMI, in the model formulation. Okay, so let's call this model, interaction model 4. Note here, all I've done is specified the formula as expenses as a function of age multiplied by BMI, so the interaction between age and BMI. So remember, when we did that with our colon operator up there, the only thing it returned was a model with the interaction term in it. All right, let's see what happens with this kind of model 4 when we run that. Okay, so what we see is we get the same model, a significant F statistic, but in terms of the coefficients, the difference in the output compared to the second model, where we use that matrix specification to only include the interaction term in the model, when we use this multiplicative specification, the model that is fitted includes each individual variable and the interaction term. So where the just specifying the interaction term using the colon operator just returned the interaction term in the model, this one, specifying using the multiplicative method, has returned main effects and interactions. Okay, so although we didn't specify the individual IVs in the formula, the model has returned the full model containing main effects and interactions. So if we were, I mean, this is a two-way kind of model, we've only got two IVs here, but if we're looking at a three-way interaction, so maybe we had age times BMI times region, then specifying the IVs as an interaction using this multiplicative method in a similar way to model 4 would return a results summary containing the main effect of each independent variable, all the two-way interactions between the independent variables, and the three-way combination of the independent variables. So when including interaction terms, it's worth noting that these can be specified for any number of variables. So we could have had a age times BMI times region times sex times another independent variable. But if when you include those, interpreting the meaning of such a complex interaction term can be very difficult. And I'd suggest that they should be really good theoretical grounds for including anything beyond an interaction between two IVs in the model. Okay, so what we've seen here, hopefully that is interesting and useful. Depending on how you specify your interaction, using stats models will depend on the model that gets fitted. If we use the multiplicative method and we just specify the interaction term, it will kind of return results for all main effects and interactions. If we use the matrix version and just specify the interaction, it will only return a model with the interaction. All right, okay, so let me summarize here briefly. When fitting multiple regression models using stats models, it is possible to include the interaction between our IVs as a term in the model. There are two ways to specify the interaction term in the model formula. The first is the matrix approach, where variable names are separated by that colon operator, so IV1 colon IV2. When this is the only IV term included in the model, then the interaction is the only predictor that will be fitted. The second is the multiplicative method, where variable names are separated by an asterisk, so signifying multiplication, so IV1 times IV2. When this is the only IV term included in the model, then the output will return main effects and interaction terms. So it will include the full model essentially for all variables that have been named in that interaction. All right, so that is the last one that I'm going to record about multiple regression. I hope this series of kind of really common classical statistical analyses and frequentist statistical analyses, I hope they were useful. Thank you for watching and listening, and I will record something else soon.